Hello everybody. In my last lecture, I have discussed about the use of rubidium and strontium in determination of the age of rocks. Now let me discuss on closure temperature and blocking temperature and the Concordia-Discordia graph. It is related to thermochronology studied in radioactive decay of uranium and Pp. So let us discuss what is closure temperature, what is blocking temperature, what is Concordia, what is Discordia with respect to uranium and lead. Closure temperature, or it is Tc. It is the temperature below which a mineral becomes a closed system for specific isotopic pair. That is, below this temperature, the daughter elements produced by radioactive parent elements are retained. So, it is the temperature below which radioactive clock starts and hence becomes suitable for correct age dating. Above this temperature, the isotopes get diffused out of the system and hence are not available for dating of minerals or rocks correctly. So, temperatures should be below the closure temperature so that in the system the daughter elements are there along with the parent elements. Daughter elements are not lost. So, it helps in correct dating of rocks and minerals. The above temperature, closure temperature, depends upon a mineral type, isotopic system such as uranium lead, potassium argon, rubidium strontium. It also depends upon grain size and cooling rate. Different systems in the same rock can give different ages. It is because larger grains retain the isotopes better. For example, zircon. Zircon contains uranium and Pp. Its temperature, closure temperature is around 1000 degree centigrade. Biotite contains potassium argon. Its closure temperature is around 300 degree centigrade. Muscovite contains potassium argon, but its closure temperature is around 400 degree centigrade. So, different systems in the same rock keep different ages because the larger grains retain the isotopes better. This property, as it varies, age becomes different. Now let us discuss blocking temperature. What is blocking? Tb. It is the temperature at which the isotopic diffusion becomes negligible during the cooling or diffusion is found to be blocked. Actually, blocking temperature is the geological reality that is controlled by history of cooling, grain size, deformation, fluids and recrystallization. Closure temperature is a theoretical concept. However, both are very often used interchangeably. One can be used for the other and vice versa. During very fast cooling, Tb is equal to Tc. Closure temperature is equal to blocking temperature. But during slow cooling, Tb is found to be less than Tc, or blocking temperature is found to be slightly lower than closure temperature. At temperature greater than Tb, the daughter and parent elements are found to be lost from the system. And at temperature less than TB, the system gets closed for loss of parent and daughter elements, and hence is useful for dating of rocks and minerals. This TB temperature is found to vary from a mineral to mineral. In case of zircon, it is 900 to 1000 centigrade. Zircon is a high temperature mineral which contains uranium at the time of its origin. It does not contain Pb, but decay of uranium produces Pb. And this decay results in two types of Pb. Uranium-238 decays to produce stable Pp206. Uranium-235 decays to produce stable Pb207. So uranium-238 has half-life period which is greater than that of the half-life period of decay of U-235. In case of U-238, the half-life period is 4.5 into 10⁹ years. Whereas in case of U-235, it is about 704 million years. So, the rate of decay is faster in case of U-235 compared to U-238. Above two decay series of uranium gives the correct age of rocks or the minerals which contain them, for example zircon, below the closure temperature, that is 900 to 1030 centigrade. And at a temperature above Tc, Pb and uranium are found to be lost from the system. So age dating yields wrong age. The above two facts, the system below closure temperature and the system above closure temperature, that yields two types of quarks. That has been discussed in the following paragraph. The above two facts are found out when the ratio of uranium 2038 with respect to Pb206 and uranium 235 with respect to Pb207 for rocks are determined. The ratio of Pb206 by U238 and the ratio of Pb207 to uranium 235 in rocks are determined, and the minerals are plotted, and these ratios are plotted in graphs. They yield curves or concordia in straight lines or discordia. Uranium-238 and uranium-235 are both found to be present in same mineral. Their decay rates are different. The comparison of parent and daughter products of above two isotopes give true age of the mineral or rock, because it has its own decay series. Uranium-235, uranium-238, they both have their own decay series. They pass through the same age. When their ratios are compared, the age is found to be correctly determined. Here it is to be remembered that some amount of Pb206 is naturally present in minerals, which will have to be removed. This is to be separated from the total Pb206 found in a mineral, so that radiogenically produced Pb206 from uranium-238 can be known. For this purpose, Pb204 amount is taken into account. Actually, Pb204 is non-radiogenic element. It is not produced by radioactive process. Its ratio with Pb206, that is Pb204 by Pb206, is used to separate out radiogenic Pb206. How? In meteorites, the ratio of Pb204 to Pb206 is known. Meteorites are formed at the same time as that of our Earth. This ratio is considered to be original ratio in minerals which are used for dating on Earth. Thus, correction is accomplished by measuring the amount of 204 in a mineral and subtracting the meteoritic proportion of Pb206 from the total Pb206 found in the rocks and minerals of the earth in order to arrive at the amount of Pb206 that has been produced by a radioactive decay process from uranium 238. So now we know what is the ratio of Pb206 to uranium 238 and we know the ratio of Pb207 to uranium 238. So they are plotted in the graph in this manner. Pb207 by uranium 235 in the x-axis and the Pb206 by uranium 238 in y-axis. And the age of rocks and minerals are being determined with respect to these ratios. This ratio gives the age of the rocks. This ratio also gives the age of the rocks. When both are found to match, for example, 0.5 giga-years, 0.5 billion years. So what is the ratio of this that gives 0.5 age and what is the ratio of this Pb206 by uranium 238 that gives 0.5 giga age. So this is this amount in y-axis, this amount in x-axis, they give 0.5 as the age. Similarly, this ratio gives the 0.1 billion years, whereas this ratio gives 1 billion years. So this is the point. This is the point for 1.5 giga-years given by Pb206 by uranium 238. This is the ratio, and this ratio of Pb207 by uranium 235 gives 1.5 billion years. So in this manner the points are plotted. And this is a curved line because the rate of decay of Pb207 from uranium 235 is not same with that of uranium 38 yielding Pb206. As uranium 38 decays at a slower rate compared to uranium 235, it is a curved line. So this line is the Concordia line which shows the concordant age, or age has been proved by the Pb206 by uranium 238 ratio and Pb207 by uranium 235 ratio. When both they indicate the same age, that point is being taken corresponding to their ratios. So this concordant graph or Concordia curve shows the locus of points having same age that are detected by the isotopic ratios of uranium 238 corresponding to Pb20 and its corresponding daughter Pb206 and uranium 235 yielding Pb207. So uranium Pb Concordia plots showing sample ages as function of Pb206 by Pb206 by uranium 238, Pb207 by uranium 235 ratios, and the samples with lower values on the Discordia. We have a straight line, that is Discordia. It is not curved because it indicates a particular age at which the temperature became more than that of the Pb, as a result of which some amount of Pb is found to be lost from the system. So it gives rise to Discordia line. Concordia represents safe radioactive clock. Discordia represents disturbed clock. So the Concordia curve is plotted by taking into account the ratios of Pb206 by uranium 238 ratios, Pb207 by uranium 235 ratios corresponding to the same age, or that is concordant age. As the rate of disintegration is slow for uranium 238 compared to uranium 235, the graph becomes a curved line indicating increasing ages which are determined in closed systems. Each of the points on this curve indicates a unique age, each point on the curve, or we can say it is concordant age, concordant with respect to Pb206 and Pb207 corresponding to uranium 238 and uranium 235. So the age shown by Pb206 by uranium 238 tallies with the age shown by Pb207 by uranium 235. Both the values they tally. Then the point is marked on the graph. That's why the age is called concordant. Graph is, the curve is called concordant curve. This is a condition when the zircon crystal providing decay of uranium is found to be undisturbed due to its cooling below closure temperature. So if the closure temperature of the system is found to be raised by metamorphism, thermal event, alteration, that is, temperature becomes greater than Tc, closure temperature, the equilibrium in the decay of radioactive uranium is found to be disturbed. Now the ratios of Pb206 to uranium 238 and Pb207 to uranium 235 are found to be lowered because of loss of radioionic Pb. Pb amount is lowered because of loss. So their ratios become lowered. This amounts to plotting of Pb and uranium ratios in a straight line below the Concordia curve. This straight line is called as the Discordia line. It joins the Concordia curve at 2 points. The upper intercept indicates the original age of the crystallization of uranium, because this is the actual age. It is shown as T0, original age, showing crystallization of zircon below Tc, closure temperature, and the lower intercept indicates the age of the Pb loss event or when the metamorphism took place. That is at T1 during metamorphism. This happens at temperature more than Tc. If temperature becomes more than Tc, some amount of Pb is being lost from the system. At this temperature, Pb is lost in varying degrees with uranium behaving as immobile element. So Pb is found to be lost. This led to different ratios of Pb by uranium, which got plotted on a straight line to form the Discordia line with age of metamorphism T1. Actually, when samples of similar real ages T1 affected differently during metamorphism are plotted on a Concordia diagram, they fall along a straight line below the concordant age line or Concordia to form line of Discordia. So this method of dating gives perfect age of crystallization of igneous rocks that crystallize from magmas and lavas, and the time at which the rock has faced metamorphism, as a result of which Tc has been more due to metamorphism. So this is all about the Concordia Discordia graph. Concordia line indicates the locus of points having different ages corresponding to the Pb uranium ratios, whereas the Discordia line indicates a time when metamorphism took place and Tc became more, or the temperature became more than the Tc, closure temperature, as a result of which some amount of Pb is found to be lost from the system with immobile uranium. And this is plotted as a straight line with upper intercept indicating the actual age of the formation of the mineral, and the lower intercept indicates the time period when metamorphism took place. So this is all about the Concordia, Discordia and closure temperature, blocking temperature. Now we will discuss some of the problems. How to find out the decay constant. So this is the method. Decay constant is equal to 0.693 by half-life period of the element. Mean half-life, it is 1 by lambda. So lambda is 1 by mean half-life, it is 0.693 by half-life. This mean half-life is the average lifetime of a radioactive atom from parent daughter measurements. It is a laboratory method. Number of parent atoms n in a sample is determined. Then the number of decays per unit time that is being measured, dn by dt. Then using the formula lambda is equal to minus 1 by n dn by dt is used to find out the decay rate. So decay is not calculated from rocks because the decay takes millions and millions of years. It is determined experimentally in the laboratory. Rocks are used to calculate the age using the known decay in the laboratory. Experimentally it is being determined. So These are the methods by which we can determine the decay constant. Mostly it is determined in the laboratory. So now let us solve some problems. Calculate the age of the rock if Pb206 by uran 230 it is 1 by 10. This is known from the rock. With lambda, this is the lambda. So we have got the lambda, we have got the d by p or d by n ratio, daughter by parent ratio. So directly putting the formula T is equal to 1 by lambda log E 1 plus d by p, we can get the age. A given quantity of pure radioactive decay is 1 by 8 of its original activity in 207.9 days. Find the mean life of the material. So it has been given that the radioactive decay is 1 by 8 of its original activity. That means decay to 1 by 8 of its original amount means it has passed through 3 half-life periods. In one half-life period it is reduced to half, in second half-life period it is reduced to 1 by 4, in third half-life period mass is reduced to 1 by 8. So 3 half-life periods have passed, which indicates the age of 207.9 days. So each half-life period is having 69.3 days. So now we can find out the decay. 0.693 by half-life. Half-life we know 0.69. So this ratio gives the decay constant, that is 1 by 100. But when you talk about mean life, it is 1 by lambda. So average lifetime is 1 by lambda, that is mean half-life, that is 100. Now let us talk about the third problem. The decay of a radioactive isotope P produces a stable daughter isotope D. Then find out the ratio of number of isotopes D to the number of atoms of P after 2 half-lives. Radioactive isotope is P, produces stable daughter D. Find out the ratio of number of isotopes of D to number of atoms of P after 2 half-life periods. So P after 1 half-life period it becomes reduced to P by 2. After 2 half-lives it becomes P by 4. So daughter is equal to P minus P by 4 is equal to 3P by 4. So the ratio of daughter and parent will be 3:1. A radioactive substance is reduced to 4 gram from original 32 gram in 15 years. So 32 grams is reduced to 4 grams in 15 years. What is the half-life? So N is equal to N0 into half into number of half-lives. This is the formula. So N is the number of parent elements, parent atoms remaining, it is 4. Originally it was 32, N0, half into number of half-lives. But total time period is 15 years. So 4 by 32, it becomes 1 by 8 is equal to half to the power number of half-lives, or 1 by 8 is equal to 1 by 2 to the power q is equal to half to the power number of half-lives. So number of half-lives is equal to 3 now. But total time period is 15 years. So 3 half-lives have taken 15 years time. So 1 half-life will be 5 years. Find the lambda and mean life of radioactive substance with half-life 2 years. It can be easily found out by putting this lambda is equal to 0.693 by T to the half. The decay constant of radioactive substance is given. Calculate the total time taken in which 1/5 of the total amount decays. We have got the decay constant. Total amount is n0. Decay takes place to n0 by 5. N is the amount remaining. So n0 minus n0 by 5 is equal to 4n0 by 5. That has been converted into daughter. Gamma is given. So T is equal to 1 by lambda log E 1 plus D by P. So everything is known. So T can be found out. The number of half-lives required for a certain amount of radioactive substance in a rock to reduce to 3% of its original value. So N will be N0 by 100, 3N0 by 100. N0 is the original mass, N will become 3N0 by 100. So D will be N0 minus 3N0 by 100, it will be 97N0 by 100. So N is equal to N0 into half to the power number of half-lives. So by calculation, N is found to be 5 half-lives. Rubidium decays to strontium-87, the decay constant is given. If at the time of formation the system contains 8 into 10 to the 4 atoms of rubidium-87, this is N0. 10 to the 3 atoms of strontium-87, this is D0. The number of strontium-87 atoms at the end of 4 half-lives will be dash. Lambda is given, N0 is given, D0 is given. It is required to find out D, which is D0 plus D lambda. So N is equal to N0 into half to the power number of half-lives. N0 is known. Now 4 half-lives. So we get the N value we get, which is equal to 5 10 to the 3. D0 is 10 to the 3 atoms. D star is equal to 8 into 10 to the 4 atoms minus 5 into 10 to the 3, because we get N. We get N, which is 5 into 10 to the 3. So D star will be 8 into 10 to the 4, which is N0, minus this N, because N is the parent element remaining. So from N0 minus N, that gives the D star. So this is D star. So we got the D star. So the number of strontium-87 atoms at the end of 4 half-lives is equal to this D star. The abundance of isotope chlorine 35 with atomic mass 34.968 AMU and chlorine 37 with atomic mass 36.965 AMU are 75.77% and 24.23% respectively. Calculate the atomic weight of chlorine in AMU. So their atomic mass is given for chlorine 35 and for chlorine 37. Their percentage is given. So they are being multiplied, they are added up, divided by 100 to give the total atomic weight. So nuclide A decays to nuclide B through alpha and beta emissions, so that mass is reduced by 32 and atomic number is reduced by 10. Find out the number of beta emissions. Atomic mass is reduced by 32 means it has faced 8 alpha, 32 by 4 is equal to 8 alpha emissions. Atomic mass is for each alpha emission, atomic mass is reduced by 4. So 32 means it has undergone 8 alpha emissions. So atomic number will be reduced by 8 into 2, 16. But it has been mentioned that the atomic number has been reduced by 10. That means there has been alpha emission which raises the atomic number. There has been beta emission. This is not alpha, there has been beta emissions which has raised the atomic number. So the number of beta emissions is 16 minus 10 is equal to 6. Then formula for PB206 by PB204. PB204, why PB204 is used? Because PB204 is non-radiogenic stable element. Similarly, in case of SMND case, ND144 is used in the formula because it is a non-radioactive stable element. Similarly, so these are the formulas which are used for PB and ND. Mixing of, let us discuss on mixing of two isotopic components A and B. Assume two end members, component A with isotopic ratio Ra, component B with isotopic ratio Rb. They are mixed to form a mixture M with isotopic ratio Rm. They mix to form a mixture M with isotopic ratio Rm. So fundamental mixing equation, let us find out. The concentration is weighed. Let Ca be the concentration of element in A, C be the concentration of element in B. So Fa is the fraction of A in the mixture, Fb is the fraction of B in the mixture, where Fa plus Fb will be the total mixture. So isotope ratio of mixture will be Fa into Ca into Ra plus Fb into Cb into Rb by FaCa plus FbCb. So this is the formula, and based upon this formula, the problem that one problem has been found out, one problem has been solved. The problem is there are two samples A and B. Concentration of strontium in sample A is 160 ppm and that in B is 318 ppm. So strontium 87 by strontium 86 ratio in the sample A is 0.7369 and that in sample B is 0.70362. Sample A and B are mixed such that the proportion of A in the mixture is 60%. So calculate strontium 87 by strontium 86 ratio in resultant mixture. This is the question. So Rm is equal to Fa Ca into Ra plus Fb Cb Rb by Fa into Ca plus Fb into Cb. Here Ca is 160 ppm, Cb 380 ppm, Ra is known, Rb known. Proportion of fraction is 60% in A, Fa. Fb will be 0.4%. So putting all these, we get the Rm ratio in mixture we get. So this is all about some of the problems that I wanted to discuss, and I have tried my best to cover all the important aspects of age determination of rocks, including the determination of age of the earth. Thank you all for giving a patient hearing to my talk.